Okay. Yeah, so thank you everybody for coming to my talk. I'm Clara Druzgalski. I recently defended my PhD here at Stanford at the Center for Turbulence Research in the Department of Mechanical Engineering. And so I'm going to give some of the research perspective of somebody who has built a high-performance code to better understand and simulate a particular system used for water desalination. So in this talk, I'm going to talk about the HPC resources that we use, and also the design decisions in terms of code, and also the numerical algorithms that we chose in order to gain better physical understanding of desalination by a method called electrodialysis. So the motivation for water desalination, right now we're in a drought, and so especially in California, we're looking at different ways that we can use our natural resources, ocean water, and desalinate that for drinking water and for agriculture. But not only limited to California, but around the world, it's difficult, in certain areas, it's difficult to find available drinking water. So there are different ways of doing water desalination. One method is distillation. There's also reverse osmosis, which is the one that usually people have heard about. And then electrodialysis, which is the one that we investigated. And electrodialysis is not a new technology. It's actually been around since the 1950s, but there's still a lot of unanswered questions that we have on how it actually works. And so my talk is going to focus on how we can combine high-performance computing with our knowledge of applied mathematics to solve this engineering problem. So some more motivation, electrodialysis is actually deployed on an industrial scale, and the most recent one, and actually one of the largest, is in Barcelona, Spain, that produces 257 million liters of water per day. And those just came online very recently in 2007 and in 2009. But the nice thing about electrodialysis is that it's not just limited to large-scale operations. So here is actually a portable electrodialysis system from General Electric. And so if you need to quickly set up one of these water desalination systems in a disaster zone or in a remote town, then you can do so. Also, if you're living in a location where you don't have natural salt deposits, such as Japan, electrodialysis is also used for salt production. And there are a lot of very interesting up-and-coming biomedical applications for it in terms of microfluidic devices. So mechanical engineering, and particularly at the Center for Turbulence Research, we use high-performance computing for fluid dynamic applications. And usually with fluid dynamics, you think about flow around an aircraft, how can we make a vehicle more aerodynamic? But now we're starting to look at other problems, both in biomedical engineering, in chemical engineering, and this one in particular for water desalination. So to give you an idea of how an electrodialysis system actually works is you have a stack of alternating anion exchange and cation exchange membranes. And in an actual system, you'd have a stack of about 100 or 200 of these. So in an anion exchange membrane, that basically means that only anions or negative ions can go through, and positive ions can only go through the cation exchange membrane. So if we're desalinating water, we have Na+, Cl-. If we run the salty water through these channels and we apply an electric field across this stack, what's going to happen is that the negative ions will move out through one membrane, the positive ions will move out through the other membrane, and we'll end up with desalinated water at the end. And in an adjacent channel, we'll have a concentrated brine. So if it's economically feasible, then you would use that concentrated brine as part of your salt production process and use the dilute channel as your desalination process. So in this particular problem, we're actually not even going to look at one complete desalination channel. And the reason for this is because when we identify an engineering system that we want to use high-performance computing to better understand, we want to start with the most fundamental system that we don't understand. So the most fundamental system that we don't understand is actually less than one of these channels. So we focus on an area adjacent to one of these cation exchange membranes. And this is basically a model setup problem that has been investigated by experimentalists, by other computational physicists, and theoreticians. So if this is our desalination channel, our simulation is just going to focus on a volume of fluid adjacent to this cation selective membrane. This is what a 2D cross-section would look like. And some example dimensional values for this are a channel height. You can imagine it on the order of 10 to the minus 6 meters, so that's micrometers. And the smallest feature size of these vortices that are going to appear is on the order of 10 to the minus 9 meters, or nanometers. And the reason why I want to point this out is because sometimes when I say, oh, we're working on this fluid dynamics problem, and the length scales that we're looking at are on the order of micrometers, people ask, well, why do you need high-performance computing? When they think about computational fluid dynamics, they think about flow around an entire aircraft. But if you're doing a CFD simulation of flow around an aircraft, for example, like a Cessna, the entire length scale of that plane is on the order of tens of meters, and you probably need to resolve physics down 3 or 4 orders of magnitude to the scale of centimeters. So what matters is not the physical size of the problem, but the relative range of length scales that you have to resolve. And so in this problem, we actually have to resolve 3 to 4 orders of magnitude of spatial resolution, and then for our numerical methods to time advance accurately and stably, we also have to use a very small time step. And also to give a sense of the applied voltage in one of these systems, across one channel, we're looking at an applied voltage on the order of 1 to 3 volts. So what got us interested in this problem to begin with is that experimentalists have basically looked at the system and applied a voltage across this membrane and measured the current output. And so they end up with these 3 current regimes. And what they see is that at these very low voltages, the experiment is well described by 1D theory. So that means that these ions are moving only due to electromigration, which is the influence of the electric field on this charged particle, and diffusion. But at these higher applied voltages, the theory would continue to predict a straight line over here, but the experiments find that the current output is actually 3 to 4 times higher than what's predicted by the theory. So we had to ask ourselves, what additional physics is happening in this problem that could account for that higher than expected current density? Sorry about that. And so what experimentalists and theoreticians have figured out is that when water and these charged particles are moving through one of these channels, it's not like you just have a block of water that's simply moving to the left and you have charged particles moving up and down. The combination of the hydrodynamics and the electrostatics put you in a situation where very complicated physics arise. And so one of these physical phenomena that arise is called electroconvective chaos. And what that is basically the interaction of the charged particles, the electric field, and the fluid medium create this chaotic flow situation which affect the transport dynamics of these ions across the membrane surface. And so this 1D theory is no longer predictive. And fluid dynamics in general, when you're talking about turbulence or chaos, is inherently 3D. So we have to do a full 3-dimensional simulation, which is orders of magnitude more expensive than running just a 1D MATLAB or Python code. So now the question is, okay, we've identified that there's this mismatch between what software and what theory is able to predict and what experiments are showing. So we have to ask ourselves, okay, if we want to analyze the situation, can we use commercial software like COMSOL multiphysics, or some people also mentioned OpenFOAM or other software that's already been written, or do we have to build a high-performance code from scratch? So ideally, you would actually just use a commercial code because then you don't have to write the code and you can go ahead and explore the physics. But some of the issues with commercial software, besides some of the licensing issues that came up earlier, is that commercial codes in the numerical methods often use something called artificial smoothing, which is great for numerical robustness. Basically, when the user sets up their problem and clicks go, the code runs, it doesn't blow up, and it gives you a solution. But that solution is not necessarily accurate. And this is because this artificial smoothing dissipates small structures that are generated by this turbulent and chaotic fluid motion. The other issue is that even if you're able to use a commercial software that doesn't use these specific numerical methods, commercial codes like COMSOL multiphysics or OpenFOAM have to be general enough to handle a wide variety of problems that their user base is interested in. Some people are interested in heat transfer problems, others in optics. And the issue is that in order to handle these wide variety of problems, it limits the user's ability to take advantage of crucial time-saving algorithms. So you may be able to realistically run a two-dimensional, basically a 2D problem, but when the fluid dynamics are inherently 3D, then you have to start looking at writing custom software. So this is an example of basically an experiment, how non-dissipative numerical methods are able to match that experiment, and then the issue with dissipative numerics. And I want you to pay attention that this is actually a log scale, so this is a very large discrepancy that arises. And this was for a flow around a cylinder problem, which is a very common validation problem for CFD simulations. So for my PhD, what I did was I wrote this C++ MPI code from scratch called EKaos. And it's a high-performance direct numerical simulation code that simulates electrokinetic chaos. Basically, these chaotic fluid dynamic structures that arise in these desalination channels. And in this code, there was no artificial smoothing used. And since we were able to identify specific areas where we could use the physics to inform how we were going to construct our numerical methods, we were able to run it over 100 times faster than COMSOL on a single node in 2D. And the reason why we only ran it in 2D is because by the time we would try running COMSOL in 3D, it would basically take years for us to run the simulation, so that's just not realistic. So the EKaos code is capable of running 3D and 2D simulations. This is a snapshot from a 3D simulation. What you're looking at over here is the cation selective surface, and the green coloring is basically the concentration field. And so we can basically see that we have this chaotic fluid motion affecting how the ions are able to transport across the surface. These are movies from one of the 2D simulations. At the top, we have the concentration field. White indicates high concentration, and black indicates depletion. As I mentioned, this is a simplified problem, so we don't have any crossflow here. So before you even have introduced any more complications of actually having the fluid move through one of these ion channels, we can see that just by applying an electric field across this system, we already have chaotic fluid motion that's generated and affecting how these large-scale structures that are bringing in high concentration fluid to the membrane surface are then affected by these smaller scale vortices that can basically help or inhibit salt moving through that surface. And at the bottom here, we have the charge density. Charge density is actually the concentration of the positive ion minus the concentration of the negative ion. And what that indicates is how large the body force will be. And so we can see that the majority of the body force is near this membrane surface. And we have a lot of very small structures. So it's important to resolve that in order to get an accurate simulation that can actually predict mean quantities that experimentalists are seeing. So here's an experiment. This experiment was actually done in 2015. This came out after our CFD simulations. And so what we see here is they also had a cation selective membrane. And when they applied an electric field, they have these tracer particles that get entrained in these chaotic vortices. And this was actually a great result for us because we had actually predicted this chaotic fluid motion before the experiment was done. And so a lot of times in the fluid dynamics community, there's a little bit of, I don't know, not an argument or a war, but sort of like a discussion between the experimentalists and the computationalists of, oh, you always have to run an experiment. Oh, well, maybe our simulations can predict it before the experiment. And while you always need experiments to verify that your models are actually indicative of reality, it does cut down on the number of experiments and the cost. So that's why companies, Boeing, many Formula One race car designers use CFD so that they can minimize the amount of time that they spend in the wind tunnel refining their designs. And so we basically want to bring this to other engineering domains like electrodialysis. So we saw that, okay, we had a simulation with, chaotic vortices. The experimentalists also had chaotic vortices, but how do we know that the simulation is actually matching the experiment? So we did a one-to-one comparison, and on the left-hand side, it's seeded with tracer particles. At the top is the experiment, the bottom is our simulation. As time goes on, these tracer particles become entrained in these vortices and start tracing out this, basically the different size vortices that happen and how they coalesce and break apart. But then really, if you wait a long enough time, because these tracer particles are charged, they have a slight charge, both in the experiment and the simulation, we actually see that we get these same depletion zones. And so we're actually able to predict that these depletion zones are going to happen, and then that can influence design decisions of engineers. For example, if you're engineering one of these desalination channels, you may want to introduce surface patterning at specific length scales so that you can encourage vortices of a certain size and improve the rate that you're desalinating your water. That way you can use less energy or desalinate a particular volume of water faster. So from our 2D simulations, which we ran just because they're a lot faster to do and we could do more of them, so we ran 5 different simulations at 5 different voltages. These are actually non-dimensional voltages, which if you do computational fluid dynamics, you tend to do everything dimensionlessly. But in the dimensional sense, we're looking at less than a volt to about 3 volts. And what we see is that as we increase the voltage, we end up with more chaotic behavior. But the important result is that if you remember, I said that the experimentalists, when they use the 1D theory would continue to predict this flat line. Whereas these points are from our 2D direct numerical simulation, and they actually predict this higher than expected current density. And so even with just a 2D simulation, we're already doing significantly better than what was done before. So over here, I've actually overlaid the experimental data in red, and then our 2D simulation in black. And I don't want to make a claim that this is a one-to-one quantitative comparison, because the geometry was different, and also the valence of the ions were different. But we can see that we're on the right track with improving our simulation and prediction capabilities by even going to a 2-dimensional scenario. So here we have our 3D EKaos simulation. What we're looking at is this plane here is the membrane surface. White, again, indicates high salt concentration. Black indicates depletion. And so what we see is that the majority of this membrane surface is actually areas of very low salt concentration. You see that most of the area is dark. And so again, this brings up the question of, well, what ways can we engineer one of these membranes so that we can get more white areas, which means that we're increasing the throughput of salt through that membrane. So one of the things that we do is we want to compare the 2D and 3D simulations so that we can see if it's possible to run maybe many quick 2D simulations instead of going to a full 3D simulations, because 3D is significantly more expensive. And so in our comparison, these are snapshots, cross-sectional snapshots, and they basically tell us important information on the basic physics of how these vortices actually appear, and informs us on how we can move forward in design decisions that would increase the throughput. So here we're looking at one of these small structures, and then we're able to basically go through our data and say, oh, okay, well, that's an interesting structure. What else can I learn about it? How did that appear there? Why is it that length scale? So we can go through our data and pull information on the concentration, on the electric field, and on the charge density, and then actually recognize that from this data, we can answer questions about how these actually appear. So in this example, we recognize that we have in the same area that we have these, what we refer to as charge density ribbons, we also have very large concentration gradients. And we also have very large gradients in the electric field. And then through Gauss's law, we can recognize that the combination of these concentration gradients and these electric field gradients result in these charge density ribbons, which create a larger body force, inducing more of these vortices. So we can ask ourselves, okay, if we're in a situation where we want to maybe depress the fluid motion or encourage mixing, what are some of the ways that we can encourage or discourage these structures from appearing? One of the things that we also look at is different average quantities to better understand how our 2D and 3D simulations compare. So here we're just looking at the mean concentration field in the surface normal direction. So that's in the direction going away from the membrane. And what we see is that we have about a 30% deviation in the prediction of the concentration in a region very close to this membrane surface. So what that indicates to us is that even though 2D simulations do a significantly better job than the 1D theory, it's still important to go the full length and run these high-performance 3D simulations in order to truly inform us on being able to predict these mean quantities accurately. So one example is the 3D predicted the current density 7% higher than 2D, which doesn't sound significant, but if you're desalinating hundreds of millions of liters of water per day, having a 7% improvement in the prediction of the current density can actually lead to a lot of cost savings. So how large are these 3D simulations? In this current version of the code, we have, in order to basically run one complete simulation where we have enough statistics in order to determine these average quantities, we use 165 million mesh points. That's over 1 billion degrees of freedom because we have 7 variables that we're identifying. In order to get the converged statistics, which in dimensional time is actually running a simulation for maybe a microsecond, it takes 100,000 time steps. And that takes about 3 weeks to actually run the simulation. And one of these generates around 11 terabytes of data, which then have to be post-processed. So the question is, why is a simulation of just one small section of a desalination channel so computationally expensive? I kind of answered this before when I talked about how the computational cost is determined by the range of relevant length and time scales that must be resolved. But the other issue is that we have to be wise in our choice of numerical algorithms and the way that we actually solve these equations. Because it's true that we have these, big supercomputers. We can ask for more resources. We can probably get them. But if we can't scale up our codes, or if we can scale up our codes but we're needlessly wasting resources, we're actually just not being, clever about the way that we're utilizing the resources that we do have. So in this part of the talk, I'm going to change gears a little bit, and I'm going to talk about the details of the numerical algorithms. This part is very mathematical and maybe very academic, but for the people who are interested in numerical algorithms, I think it's worthwhile to understand how the thought process of how we can use our understanding of physics to actually simplify the mathematics and then end up with a much higher performance code just through a wise choice of numerical algorithms. So in order to build one of these fluid simulations, you have to look at the governing equations. The governing equations in this case are the species conservation equation, which is the time evolution of the positive ion, and the time evolution of the negative ion. Then we have the Navier-Stokes equation, which is basically how the velocity field or momentum changes in time. So in 3 dimensions, we have u, v, and w. Then we have Gauss's law, which relates the distribution of the free charge density to the divergence of the electric field. And by combining all of these equations and solving them directly, this is what allows us to actually predict what's going to happen in these desalination channels. So we have a set of boundary conditions to model the ideally cation selective surface. We impose a no-flux condition on the negative ion, so that basically means that anions can't go through here. And on the other boundary condition, we have a stationary reservoir. That basically provides an equal concentration of the positive and negative ions. And in the other directions, we have periodic boundary conditions. And basically, sometimes when I say periodic boundary conditions, it's like, oh, well, is this an academic exercise? Not really. I mean, this is basically, if you have a long channel, then at least locally, that domain is infinite. So those equations are presented in a dimensionless form because this basically allows us to reduce our parameter space and generalize our problem. And this leaves us with 5 parameters, which, as we tweak them, have different consequences in terms of the physics and also the mathematics. So we have this one particular parameter, epsilon, which we refer to as the screening length. And this is basically a smallness parameter. And so as we decrease the size of this epsilon, we have to use more computational resources by orders of magnitude, even though it's more representative of the problem. So we have to choose a parameter space that allows us to be wise about the computational resources that we do have, but is still representative of a physical problem. And then as we improve this code and use more better numerical methods, then we can get closer and closer to simulating one of these, an entire desalination channel. So for the spatial discretization of this, the 3D code has over 165 million spatial grid points. So that means at each point in time, we're solving for all the variables at each of these points. We use a staggered mesh configuration, a non-uniform mesh in the membrane normal direction, and then for the discretization, we use a second-order central finite difference scheme. The time integration that we choose is we have the species conservation equations, Navier-Stokes, and Gauss's law. And for now, we're just going to focus on these top species conservation equations. So the math that I'm about to go through, if you're familiar with linear algebra or partial differential equations, is basically going to show you how we can use physics to inform how we can choose our left-hand side operators and make them more computationally efficient. And if you're not into partial differential equations or linear algebra, that's totally fine. I think it gives you a perspective of how engineers use applied mathematics in order to better utilize high-performance computing resources. So what we do is we start out with a particular time advancement scheme. This is second order in time, which means that we handle all of these terms on the right-hand side at time step n+1. And this is very useful from a numerical stability perspective because basically then we have more freedom in the choice of our time step. But the problem is that this makes our left-hand side operator more complicated, and this means that when we're solving AX equals B, inverting that operator is a lot more demanding. So what we can do is we can use our knowledge of the physics and recognize that actually most of these terms we're going to have to use a time step that resolves the fastest unsteady physics. But if some of the physics is so fast that basically the rest of it doesn't have time to react, then we can choose an intermediate time step and then basically advance our simulation an order or 2 orders of magnitude faster. So we handle 2 of the terms at this future time step, and the rest we handle them at time step n. But the problem with this is that then we've committed a first-order approximation. So our algorithm is no longer second order in time, which means second order accurate. We've actually reduced the order of accuracy. But we can do other, basically numerical, use other numerical insight to recognize that if we put this in an iterative form, that with 2 iterations, we're going to be able to obtain our second-order numerical accuracy. Now, this left-hand side operator has become drastically more simplified, but it's still nonlinear, and we still have directional coupling, which means that it's still very expensive to solve. So what we can do is we can recognize that it's possible to linearize this term and end up with 2 additional terms. And then, when we write this in what we refer to as delta form, this left-hand side operator actually goes to 0 as we converge. So from a computational perspective, it gives us a sense that our algorithm is actually converging. Now, after we have this written in delta form, at this point, since our left-hand side operator is linear, we could actually just use our favorite AX equals B solver and solve the problem. So we could use LAPACK or some other math library to solve it. But recognizing that we actually have a high bandwidth matrix and that this is going to be more computationally intensive to solve, we recognize, well, we have an iterative algorithm anyway. We have a lot of freedom in how we design, our left-hand side operator. So let's do something a little more clever and use physics to inform our design decisions. So one of the things that we can recognize is that we can actually move some of the terms to the left-hand side and neglect other terms. So if we basically move a few of the terms to the left-hand side, these are the electromigration terms, we can cancel one of them because the physics have basically smaller eigenvalues, so they're less stiff. And then we end up in a situation where we've actually transformed this very complicated expression into something a lot more simple. And then by using Gauss's law, we can do an analytical substitution and end up on our left-hand side with linear terms and only with concentration as our unknowns, so C plus and C minus. And basically what that means is that this ends up being a pentadiagonal matrix, which we can use an order n algorithm to solve. So in doing this operation, we basically made the left-hand side operator linear, and now it only involves local coupling between the positive ion and the negative ion. So now that we've solved the concentration equation, we still have 3 more equations, which I'm not going to go through in significant detail, but just to say that all of these equations end up being elliptic in nature and that we can use the same numerical algorithm to solve it. So we use something called a pseudo-spectral solver. And the advantage of this is that basically, since we have been informed beforehand that we know that we need to parallelize this because it's a very large problem, in using a pseudo-spectral solver, we can actually decompose our domain onto the different processors and solve independent tridiagonal matrices. So when we're solving all of these equations, at each iteration, we're basically solving 5 million independent tridiagonal matrices distributed across the different processors. To complete an entire time step where we have to do 3 iterations, we actually have to solve 15 million independent tridiagonal matrices. So by taking advantage of this geometry, which is simple compared to, say, flow around an aircraft, and using physical insight, we were basically able to reduce the matrix bandwidth, which enabled us to use fast and robust math libraries like FFTW and LAPACK, which are also portable. So if we wanted to run the simulation on different clusters, not just the ones at Stanford, but ones at national labs, we're able to do so. And finally, we're able to reduce the communication costs across these processors because we designed the algorithm with parallelization in mind. We were able to decompose this into independent tridiagonal systems, which we distributed across the different processors. So in conclusion, we developed this simulation to basically better understand desalination channels. we guided our design decisions of the numerical algorithms but through our understanding of the physics. And we're able to predict, actually improve the prediction of values that experimentalists had found. And we actually saw that we could learn more about the fundamental physics about how this generates structures that are similar to turbulence, and also how the 2D and 3D simulations compare and can inform design decisions down the line. So thank you very much. If anybody has any questions, I would be happy to answer them.
I have two questions.
Sure.
I was wondering if you tried out before doing this one, you tried modeling, right?
If we tried what?
We tried modeling, turbulence modeling, right? Using
Oh, similar to turbulence. Oh, so turbulence modeling. So, for example, like large eddy simulation.
No, not large eddy simulation. Just a simple turbulence model, like something.
Yeah, so some of these turbulence models, like K epsilon model is one of them. So the physics of this is actually fundamentally different because this, even though it's a chaotic flow phenomena, is not turbulence. Turbulence is high Reynolds number, and so it actually generates structures that are fundamentally different than at this lower Reynolds number regime. So some of the models that, that turbulence uses have guided our design decisions in the choice of numerical algorithms, and we're actually looking at turbulence models to see, oh, is there a way that we can design faster models for these chaotic but non-turbulent scenarios. Yeah, and your second question?
Yeah, the second question is, from this analysis, were you able to put together some kind of parameters for efficiency of the desalination?
So we don't have parameters for efficiency of desalination because, as I mentioned, the purpose of this particular code at this point in time was to zoom in just next to a cation selective surface. So that's not even the full desalination problem. So we wanted to inform designers of actual desalination problems about what parameters they want to look at. We actually have to go to a larger problem and use more computational resources. So no, we haven't been able to do that yet. Basically, the people who pick up this research will do larger simulations and add the complexity that's needed for that. Yes?
Yeah, just a couple quick ones. One, what was the target hardware that you parallelized this on? And two, what was the utilization you were getting out of that hardware with these choices of algorithms? And three, you talked about using a finite difference approach. That's implying that was it a kind of a regular grid or because I thought in one of the slides it said that you were using some kind of unstructured or no?
No, it's not unstructured. It's staggered. So it's a structured grid. So staggered is just that you're having you're actually calculating the velocity and then the gradient of the pressure at the same node location, as opposed to unstaggered where.
So what was did you consider going to a fully adaptive method? Unstructured adaptive, so you can be more intelligent where you discretize and where as your residual starts increasing, you locally add resolution.
Right. So there's some like adaptive mesh refinement techniques, AMR. There's also
fully unstructured is what I'm asking.
Yeah, fully unstructured. Okay, so for this particular problem, we actually didn't need to because we know beforehand that our sharpest gradients are going to be close to the membrane surface. So we use a non-uniform mesh in that direction so that we could concentrate the grid points there. If you're analyzing this on a more complicated geometry, like let's say that we, well, I mean, even then, I mean, the nice thing about these desalination channels is that the sharpest features are always going to be near the membrane surface because that's where you have the largest body forces and the most, like the largest kinetic energy.
Independent things like going on or anything like that that could cause it to be something where you need the fully adaptive, right?
Well, yeah. So basically, what I'm saying is that you can predict beforehand where you need to concentrate your mesh points, and so you don't need to go that because that adds additional computational cost. So for example, if you're doing a combustion simulation where you can't predict beforehand where your smallest structures are going to appear because you basically have an explosion, it could appear anywhere. then that's where adaptive mesh refinement is actually really useful and important. But it's not useful for every problem. Yeah. And then you had other questions.
Yes, the target hardware and the utilization you got.
Okay.
Choice of algorithms.
Yeah, so the hardware that we used was actually the Certainty cluster at Stanford. So this was multi-CPU code, so this was parallelized only with MPI. And then in terms of, checking the scaling, I mean, basically the issues that we ran into was that what was limiting us from scaling this to a larger problem was the availability of fast Fourier transform libraries, which give you total freedom of domain decomposition. So FFTW, which probably a lot of you are familiar with, doesn't give you total freedom of that domain decomposition. So we had to use a Sandia library that basically wraps around FFTW. And then it was because using that FFT library was what prevented us from scaling to even larger problems.
Did I/O come into effect at all? You said it was, what, 13 terabytes?
Oh, 11 terabytes. Not compared to the runtime, because we would only write to disk every 100 time steps, and that was sufficient. So, I mean, when we did write to disk, then, I mean, obviously we did see, the decrease in performance, so it took longer. But the vast majority of the time was not spent in I/O. As we scale this problem up, that will become more and more of an issue. Yeah. Any other questions? Yeah?
Were there any challenges that you faced in trying to get the most out of the system that you could, that could have been resolved for you with additional software or additional hardware? What were those? What would have helped you make better use of the system, faster use of the system?
A better fast Fourier transform libraries. That was really the bottleneck. If we had, and that was a bottleneck not just for me, but for other people who were doing fluid dynamic simulations in my lab, is just having better, faster fast Fourier transforms. Because fast Fourier transforms are very expensive because it's an all-to-all operation. So there's a lot of communication overhead to that, and it doesn't scale up as well as some of the other algorithms. One of the nice things that we were able to do is actually, when we were solving the tridiagonal matrices, these were actually small enough that and independent. So we didn't even have to use ScaLAPACK or some parallel linear solver. We were actually able to use serial linear solvers just distributed in parallel. So I used LAPACK. It runs very fast. Is there another tridiagonal? I mean, tridiagonal matrix solvers, I mean, they already solve, they're already very fast and well known. I don't know if there's something better than LAPACK, but it does the job. So, okay. Thank you very much.